Hello everyone. In this lecture, I will discuss about the temperature stresses in uniform bars. When the temperature of an object change, its dimensions are changed. Let us consider initially temperature of the object is 100 degrees and after some time temperature of the object is increased to 150 degrees centigrade. So here temperature is changed from 100 to 150 degrees centigrade. Then the object is expanded. So if the temperature of an object is changed, its dimensions also changed. Let us consider a block of homogeneous and isotropic material that is free to expand in all the directions. So let's see in the figure. And if the block is subjected to uniform changes in temperatures, let us consider change in temperature capital T. The sides of the blocks will be increased and will take the shape is shown by the dotted lines. So with corner C taken as the reference point. Here these dotted lines are represent the increase in dimensions of the block due to the change in temperature. We know that change in dimensions of the object is directly proportional to the change in temperature, that is the capital T. So we have to state that one thermal strain is directly proportional to the change in temperature, that is capital T. So here let us consider epsilon T is the thermal strain. So we have to write down epsilon T is directly proportional to the capital T, and also have to write down that one epsilon T equal to the alpha into capital T. Here alpha is the coefficient of thermal expansion or thermal contraction. So generally it is the property of the material and has a unit reciprocal of the change in temperature. So units of the alpha is 1 by kelvins or 1 by degree Celsius. Generally the value of the alpha is, for the steel material, it will be vary from 10 to 18 into 10 to the power minus 6. So units are the 1 by degree Celsius. Similarly for the copper material is 17 into 10 to the power minus 6 per degree Celsius. For the aluminium and its alloys is 23 into 10 to the power minus 6 per degree Celsius. And here let us consider a bar of length capital L subjected to uniform temperature increase. So change in temperature is capital T. The bar is free to expand. Let's see in the diagram here. The bar having the capital L and change in temperature is capital T. And one more thing here you have to see that one. The bar is freely expanding. So here delta T is the free expansion of the bar due to change in temperature capital T. And we know that one deformation or change in length. So previously we are concerned that is the deformation or maybe change in length, that is the delta equal to the original length into the strain. Same thing here also, deformation due to the temperature changes, that is the delta T equal to, we have to write down the original length into the thermal strain. So delta T equal to the epsilon T into capital L. Previously we know that one epsilon T equal to the alpha T. So the deformation due to the temperature change, that is delta T equal to the alpha T L. So this is the very important formula. Kindly you have to remember this one. And one more thing is very important you have to remember. So when the bar is free to expanding, there is the no thermal stresses are generated in the bar. So why mean there is the no restriction for the deformation. So there is a no restriction for the deformation mean. So it is a freely expanding. So no thermal stresses it will be generated. It's a very important for the all the competitive exams. So kindly remember that one. If the bar is free to expanding, there is the no thermal stresses. Let's see the second condition. First one is the bar is free to expand. In this condition, no thermal stresses are generated. Let's see the second condition. Consider a bar AB having the length L fixed at the ends. If the supports do not yield, the bar is not free to expand by the amount delta T, and it will be subjected to thermal stress, that is the sigma T. The value of the sigma T is given, that one. Sigma T is the thermal stresses. We know that one. Stress equal to the strain into Young's modulus. Similarly, here also thermal stress, that is the sigma T equal to the thermal strain, that is the epsilon T into the E. We know that one. So thermal strain is nothing but deformation divided by the original length. So deformation we are considering here delta T. So delta T, we have to write down the thermal strain equal to the, that is epsilon T equal to the delta T divided by L. So thermal stress sigma T equal to the delta T divided by L into the E. Previously already we discussed that one. That is the thermal strain. Epsilon T also have to write down that one. Alpha TL. So thermal stress equal to the alpha TL divided by E by L. So L will cancel. So here thermal stress, that is the sigma T equal to the E alpha capital T. So this is the second formula. We have to remember that one. Previously we discussed that one. Formula for the thermal strain. Here we have to remember that one formula for the thermal stress. And one more thing you have to remember that one. The nature of stresses is compressive when the change in temperature is positive. Similarly, nature of the stresses is tensile when the change in temperature is negative. And one more thing you have to remember that one. These thermal stresses, that is the sigma T's, not depend upon the cross-sectional area. And one more thing, we have to see this one. Third condition. So here in the diagram we have to observe that one. The bar AB having the length L. So which one of the supports is yields by an amount A. So this is the yielding. So the amount of yield is small a, let us consider. In this case, the total amount of expansion E, it will be delta T minus A. So the resulting thermal stress sigma T is given by sigma T equal to the alpha TL minus A divided by EL. So this is the third formula we have to remember.